Okay, so part three here. Let's think about a little circuit with a battery. The battery gives charges potential energy. It's like a log flume ride at Kings Island. It lifts them up in a sense. And then as they flow back down, we can get work done out of it. Like water might turn a little water wheel here, but we can use the charges to turn a fan blade, let's say. Something might bother you in this little animation. Last week, we kept saying the positive charges never move, and that is still true. So what's going on with this picture? Well, we knew about electricity long before we knew about protons and electrons. And we didn't know, actually, when we studied this, if the positive charges were moving one way or if the negative charges were moving the other way. So we just guessed that the positive charges were moving. And we got it wrong. We didn't know it was actually the negatives moving the other way. But it turns out it doesn't actually matter for how you think about these problems here. So we can just think of it when an electron jumps from one atom to another, we can think about the positive ion moved the other way. So anyway, we in physics, when studying electricity, and if you become an electrician, we think of it as if the positive charge is moving here. So here's a battery. It's a 12-volt battery. We'll call the positive end A. There's a wire here that runs over to B. A light bulb's on the other side is point C. And then the wire flows back down to the negative terminal at point D here. We say that there is a potential difference, that's a voltage, of 12 volts between D and A there. If we go from A to B, there is no potential difference. There's no voltage from A to B. In other words, what that means is the amount of energy per charge didn't change as we go through that wire, because the wire basically doesn't use any up. Now that's idealized. In reality, the wire would use up a teeny bit of voltage, a teeny bit, but we're going to ignore that for now. This right here says the difference in voltage from B to C is negative 12. In other words, as we went through the light bulb, we dropped in electric energy. We took that electric energy and we used it up to convert it into heat and light. So that's what the negative is there, a drop in 12 volts as we go through the light bulb from B to C. And then as we come back from C to D, that wire doesn't use up any energy at all, so it doesn't use up any voltage at all, is how we could look at this. A slightly different way of looking at the same picture is this. Let's say D is at 0 volts. Think of it as an elevator for the charges. When it takes us over to point A, that's like at the top of the building. That's 12 volts. Then as we go through the wire, we're still at 12 volts here. That's why there was no difference. We say the voltage between point A and B is 0 because we didn't change at all as we go from A to B. That's like walking around on the top floor of a building. You haven't changed your potential energy at all. Then it's like sliding down a slide or something. As you go through the bulb, this side is at 0 volts, so we dropped from 12 to 0 on this side. And since C's at 0 and we travel along the ground floor, kind of like on the building, to D, which is also at 0 volts, we didn't change our voltage at all. So the positive side of the battery we think of as being at the high potential, and the negative side of the battery we think of as being at the low potential there. So the battery does several things. It gives the energy. It pumps up the charge from the negative side to the positive side, we think of it as, and it maintains a voltage that pushes the charges through the circuit here. So the battery supplies energy, and then here's the external circuit. The wires use up a teeny bit, but we're going to ignore that. But a light bulb or a fan blade or something like that is what primarily uses up the energy there. Here's one more way of thinking about it. Here, imagine that here's our potential, our voltage, in other words. Here's 0 volts and 1.5. So in this case, we have a double A or a triple A battery here. As we go from D to A, it's like we go in an elevator, and that elevator raises it up 1.5 floors or 1.5 volts. As we go through the wire from A to B, we don't change at all. So it's like walking around on the ground floor. Then as we go through the light bulb, we use up all of that energy, and then we come back down to C here. So we used up our 1.5 joules of energy per coulomb. And then we travel in the wire from C to D, and that's not really doing anything at all. It's just a road, in a sense, to get the electrons back to the base there. And so no change right there. That's the